Parameters of fluid systems. So a new topic. I'll get my pen. Because we have orange. So fluids, and more specifically fluid statics or hydrostatics, which is really, it's the study of fluids at rest. So static means stopped and hydro means water. So it's the study of fluids at rest and the pressure in a fluid or the pressure exerted by a fluid on an immersed body. So it's very important in hydraulics, very important in hydraulics. And it explains why atmospheric pressure changes with altitude, why wood and oil float on water, and why the surface of still water is always level. So it's quite an important thing to understand. You can do whole degrees on this type of stuff. Been around for quite a while, since antiquities, which is quite a long way away. So Pythagoras did a bit on it, Pascal did a bit on it, and you should all know roughly what Archimedes did. And he was BC, so you know. So it's been around for a while. There are two types of fluids that we talk about. There's incompressible fluid, which are liquids. So, you know, the mass of the fluid, you can't squash a liquid, can you? You can't squash it. You can't make it smaller. The mass will stay the same. And the volume will remain the same regardless on the pressure. You try squashing a water in a jar or something, right? So incompressible fluids, liquids, and a compressible fluid is a gas or a vapor. And those are the ones, I mean, you can't squash a gas because a gas will tend to fill any vessel. And depending on the pressure that you put a gas under, has a considerable change in volume and temperature as well. So compressible fluids are gases and incompressible fluids are liquids. So hydraulics, you know, liquids, that's how we move things with hydraulics, because we can compress it and it moves elsewhere. And a compressible fluid is also a gas. So obviously, you know, something like a turbine jet engine, you've got to be able to compress the gas. You know, your car will compress air or compress gas to make things happen. Obviously, in this tutorial type thing, you know, and in mechanical principles, we'll be talking about fluids. So when we talk about hydrostatics, we'll be talking about fluids, and that can be oil, water. Right. Main two things. So a couple of things we need just to make sure we know about density. We should all know what density is. It's how much matter there is in something. So density is the mass per unit volume. And the formula for density is mass over volume. So it's mass per unit volume. So if something's really, really dense, it's got a lot of mass and a small volume. So density is mass over volume. Mass is measured in kilograms, volume is measured in cubic meters. So the unit of density is kilogram per cubic meters. And just so you know, the density of water is 1,000 kilograms per cubic meter. So density is mass over volume. The symbol for density, by the way, is that. It's like a weird P. It's not P, right? That's a P. That's called rho. That's a symbol for density. So when you see it down next, that's the symbol for density. Mass over volume. Obviously, you can rearrange this formula. You can rearrange this formula to find volume and also mass. So you'll see it like that. Density is mass over volume. Density of water is 1,000, and a relative density is comparing the density of a substance to that of water, because water is all over the place. So the density of a substance, right? relative density of a substance is comparing it to the density of water. So relative density, which could be a number, times by the density of water will give you the density of that substance. For example, the relative density of oil, I put oil in a bracket because there's loads of different types of oil, but the relative density of oil is 0.9. So say if you wanted to work out the density of whatever that oil is and all you were given was 0.9, you could work out the density by comparing it with density of water, and there's the formula. So it's the relative density times by the density of water at, density changes with height, right? So things like that. So density of seawater, for example, is 1020. So relative density times by density of water. So if I get relative density of oil is 0.9, to find the density of that oil, I'm just going to multiply the 0.9 by 1,000, which gives you 900. You should have to do that on the calculator, but to show you, obviously. So the density of whatever oil this is 900 kilograms per cubic meter. That is why oil floats on water, because it's a bit lighter. So density is mass over volume. That's the symbol for density. M is mass, V is volume. And if you've got to work out relative density, that's the formula. So that's the density. Pressure, we'll have to talk about pressure. So here is a piston with a fluid in it. Obviously hydraulics works by, if you compress this or you push this, right, that fluid there will cause a force on this and your piston can go in and out. So the pressure on here, let's go to yellow. The pressure on here is the force exerted per unit area. We'll ignore the weight of the fluid. So there's a fluid in there which is causing a pressure, which is causing a force. So if you put a force on here, there's going to be a pressure coming back this way, ignoring the weight of the fluid. We should all know that pressure is force over area. So water pressure, tensile pressure, tensile stress is all force over area. Force is Newton or per square meter. So the unit of pressure is going to be a Newton per square meter, or we use Pascal. So 1 Newton per square meter is also 1 Pascal. And you will probably find that the pressure we're talking about are quite big. So you'll have, let's get a different color. You probably have kilopascals or megapascals or gigapascals, because a Newton per square meter is quite a small unit. So the unit of pressure, water pressure, pressure at depth is going to be in pascals or newtons per square meter. And if you've got a water pressure, you've also got a force. So if you go diving, the pressure builds up, which causes a force. You may also see it, depending where you are, the weather forecasters use bar as unit of pressure. You may also see PSI, pounds per square inch, if you're in America. But the SI unit is a Pascal. But you may also see bar if you're pumping your tires up. So 1 bar is 1 times 10 to the 5 Newton per square meter, or 1 times 10 to the 5 Pascal. So atmospheric pressure at the moment is 1 bar. And really we're designed as a human race to withstand that pressure. You go to other planets and the pressure goes up. So pressure in a fluid, which is the main topic really, we need to work out what is the pressure in a fluid, because that can cause us problems or can help us out. So if you've got a container with a fluid in it, the pressure in the fluid acts equally in all directions. So the fluid, the pressure there is equal, it's the same, so the pressure in all directions. The pressure exerted on a surface is normal to the surface, so it's like 90 degrees to it. That means normal, so There's a pressure there, there's a pressure there, there's a pressure there, pressure there, pressure all over the place, normal to the surface. Any 2 points in horizontal plane, pressure is equal, which means the pressure there is the same as the pressure there. Let's go to, so the pressure there is the same as the pressure there. Obviously, because you've got more depth here, the pressure, the green bit here is going to be less pressure than the purple bit, because you've got pressure at depth. The further you are down, the more you are. Right? This is at rest, by the way, fluid at rest. So the pressure at depth is what we're after. It means to work out the pressure at a certain depth. So consider a column of liquid. So all this is a column of liquid. So there's my liquid. Could be a round tank or a square tank. So this liquid in here, which is in here, look, has got a liquid of density rho, so some sort of density. It's got a pressure, because it will, that stays closed and full up. So this pressure here, this water pressure, is causing a pressure here. Right? That's where the most pressure is going to be at the bottom. It's also got a height in meters. So the deeper you are in something, the more pressure you're going to get, because you've got all this on top of you. So we're trying to get a formula now for the pressure at depth. If you're a diver, you need to know how much pressure you've got at a certain depth of water. So volume of liquid, we know volume. The volume of this liquid is going to be the area, right? That could be square or round, times by the height. So the area times by the height. So volume of liquid, so the volume of the liquid in there is going to be this area here, right, in 3D, times by the height. So if it was a round cylinder, you'd have a circle. So the area of that circle times by this height would give you the volume of liquid. We know the density of a liquid is mass over volume from up there, look. So the density of that liquid is mass over volume. I've rearranged that, so the mass of liquid is the density times by the volume. Density of the liquid is mass over volume. I've rearranged that. That means therefore 3 does. So therefore the mass is going to be the density times by the volume. So that's the symbol for density, and we know that's volume, A times H from up here. So the mass of the liquid in that container is density times by the area here times by the height. So because we've got a mass, we've also got a weight, which is going to be F, because that mass of liquid will have a force due to gravity. So F equals ma, which you should know, ma. So m being the mass, which we know is this, and a being gravity, acceleration due to gravity. This liquid here is being pulled down by gravity, and we know that gravity is 9.81. Acceleration due to gravity is 9.81. So the weight of the liquid, or the force of the liquid, is m times a. There's your m, because it's there, look, mass of liquid. There's your m, times by g is gravity. So the weight of this liquid is density, area, height, times by gravity. So we know now the pressure on the base. So the pressure here, at that point, the pressure is going to be force over area, because we know that from up here, pressure is force over area. So the pressure at that point is going to be force over area. So the pressure on the base is force over area. Well, we know that the force let's get the right thing, red. So the force we know is this. So there's my force here, density, area, height, gravity, because that's the force there, look, m times a, that gives me the force. So the force is density, area, height, gravity, all divided by the area of this again. Luckily, there's an area there and there's an area there. So the areas cancel out, which then gives us a formula. The pressure at depth is rho GH, which is density times by gravity times by height. So if you've got a tank and you want to know what the pressure here is, and you know the density, and you know the height, you can use this formula to work out the pressure at a certain point. Rho GH, density, gravity, height. So that's what you need to remember for pressure at depth. So examples, there's some examples using this formula. So for example, I've got density salt water of density 1020. I'm saying 3 meters down on Earth, so gravity is 9.81. What would be the pressure 3 meters down? Well, the pressure is rho GH. Right, this is density, which is 1020. Gravity is 9.81, and the height is meters. So the height's always got to be in meters, gravity's got to be in meters per second, and the density's always got to be in kilograms per cubic meter. So pressure is density, gravity, height. That's my density there, look, 1020. There's my gravity, there's my height. Whack it in your calculator. 1020 times by 9.81 times by 3 gives you 30018.6 pascals, or if you press E and G, gives you 30 kilopascals. So the pressure 3 meters down would be that much. In water, so I've done the same here now for oil, because you know water and oil don't like each other. So same situation, what would be the pressure now 3 meters down in oil? Bearing in mind oil is less dense than water. So same thing, 3 meters, rho GH, that's my density of oil. Gravity is 9.81 and we're still 3 meters down. Obviously it's less dense than water, so 900 times by 9.81 times by 3. 26487 pascals, or 26.487 kilopascals, same thing. So there's less pressure in oil. That's why they float, really. Nice and easy. Number 3. So this one we've got density again. We're in water, and at some point here we've got a pressure of 40 kilopascals. So you could have a gauge measuring that. We need to know what height would you get to a pressure of 40 kilopascals in salt water or seawater, 1020 density. So we need to find the height this time. So we know pressure is rho GH. We need to find the height because we don't know it. So I've just rearranged this formula to find height. So leave the H over here, bring the density and the gravity down. So pressure is density over gravity. So height is going to be pressure divided by density times by gravity. So there's my pressure, 40 kilopascals. There's my density and there's my gravity. So do that and it'll give you the height that you need to get to a pressure of 40 kilopascals. So 40 times 10 to the 3 divided by 1020 times by 9.81. Close the brackets. Gives you 3.99 meters. I've gone to 4. So at 4 meters down in water of that density, you will get a pressure of 40 kilopascals. Question number 4. This one, I've given you a height and I've given you a pressure. So at 2 meters down, there's the pressure. What would be the density of the liquid we'd have to be in for that to happen? So calculate the density of the liquid. Again, there's the formula. I'm just going to rearrange it. I'm going to leave the density bit over here and bring the G and the H down. So pressure divided by gravity times by height will give you density. So density is going to be pressure, which is 15 kilo, divided by gravity, which is 9.81, and the height is 2. So 15,000 divided by 9.81 times by 2 will give us the density of this liquid. So 15 10 to the 3 divided by 9.81 times by 2. 764. So whatever this is, if you were 2 meters down in a liquid of that density, you would feel 15 kilopascals of pressure. So nice and easy, just using rho GH. So things to take away from today: density is mass over volume, and pressure at depth is density, gravity, and height. Density is measured in kilograms per cubic meter, gravity is meters per second, and height is in meters. So not too difficult. Have a go at them questions, and then there's some practice ones to do here. Look, so they're based on that formula really, and I've just made some examples of submarines, divers, tank full of oil, and a column of liquid. So they're using rho GH. This one here I've given you relative density, so you need to find out what the actual density is. So have a go at them, please. For a bit of practice. Any problems, let me know, and over and out.